Good evening. So let's wait for 2 minutes.
Sure, sure.
So I think we can get started. Welcome
Yes.
to session 7. Yes, so welcome to session 7, seventh week of this course on parameterized algorithms. And today we'll discuss 5 questions. So these 5 questions are from the assignment of previous year. And I suspect that today is going to be a shorter session. We'll cover all the 5 questions, but I still suspect that today we will be finishing in 1.5 hours. And if there are any doubts, any questions, any comments, we can utilize the rest of the time to discuss. So this is the first question. In this question, you are given a graph G. It has 13 vertices, and a corresponding tree decomposition of the graph is also given. So we have seen what is the meaning of tree decomposition. And the objective is to find a balanced separator of the graph whose size is at most k plus 1. What is k? K is 2. That is the width of the decomposition. So width of the decomposition is the largest bag minus 1. So largest bag has 3 elements. 3 minus 1, that is width is 2. So we are looking for a separator of size 3. So before going into the question, let me discuss what is a separator for completeness. So a subset S of the vertices is a separator if removal of S and of course the edges incident on S, on the vertices of S, disconnects the graph. So that means it partitions the graph, or rather it gives rise to multiple connected components. Then we will say that this subset S is a separator. Okay, so that is the definition of separator. Now, but now what is a balanced separator? So balanced separator means, let's see diagrammatically. Let's say this is the graph. So you deleted some portion of the graph, which is S, and let us say you got two components, one component on the left side, one component on the right side. So let us say this is component 1 after removal of S, this is component 2 after removal of S. Then if both the components have less than n by 2 vertices, then sometimes less than equal to is also accepted. Then we will say that S is a balanced separator. So that means it is not breaking the graph into a heavy piece and then so all the pieces are light. So if a component is having less than n by 2 vertices, then we will say that the component is light. And if all the components are light, then we will say that S is a balanced separator. So is the definition of balanced separator clear?
Yes, except the fact that this definition is too rigid that we need to have more or less n by 2 number of the components, I mean elements in both the components.
Okay. Okay. So why do you think it is rigid?
Okay, because we have to find, I mean, I think that for all the graphs, it won't be that much easy to find a point and whose removal will
Not a
create
point, a
two more
set
or
of
less.
vertices. Multiple. S is a subset of vertices.
Oh, I see. Yes, yes, yes.
So
Because in this example, I was under the impression that if I remove, somehow if I remove the vertex B, so then this entire graph will become disconnected, but then probably there would be some use of the tree decomposition technique as well here.
yes, yes. So if you, for example, let's delete B. So once we deleted B, all the edges incident to B are also deleted. And how many connected components are there? So P itself becomes an isolated vertex because P had degree 1. Uh, these four together becomes one connected component, S, T, A, and C. And the rest of the vertices becomes another connected component if you are deleting B. All right.
Yes.
Then the heaviest component is this component. So we have to check how many vertices does it have. So it has 1, 2, 3, 4, 5, 6, 7 vertices. So in our case, n is 13. So we will allow uh, n by 2 floor vertices, the 6 vertices in each light component. So this component cannot be deemed light. This is more than half, more than 50% of the vertices of the graph are concentrated in this component. So therefore, removing B is not, uh, so B itself cannot be considered a balanced separator. Of course, it's a separator, but it is not a balanced separator because one of the components is more than 50% of the vertices.
Yes. And can we have more than two components?
Yes, yes. We can have
Okay.
as many components. That's not a problem. So this is for the purpose of simplicity. I mean, uh, I should maybe draw some more components. So it may happen that removal of S gives rise to multiple components. So maybe S is like this. So this is C1, C2, this is C3, this is C4. So but between the components, there are no edges. So all the edges are within the components.
Yes.
Okay. So now, as you have pointed out, that this tree decomposition can be exploited to find the separator, that too of size at most k plus 1. So as soon as you see k plus 1, you should suspect that we are deleting exactly one bag. So in a bag, we have at most k plus 1 vertices. So deleting a bag means we are deleting at most k plus 1 vertices. So we should suspect that maybe each bag can act as some separator. And then the objective is to identify which bag is the appropriate bag, which bag is the right candidate for becoming a balanced separator. Okay. So how about deleting the bag corresponding to the root? So the way the algorithm is described in the video, that you start by deleting all the vertices in the root of the tree decomposition and check if that is giving you a balanced separator or not. Okay. So let me clean up things again. So deleting the root means you are deleting exactly one vertex. That is A. So A is this one. So now on deletion of A, how many uh, connected components shall we get?
Yes. So if we delete from A, then we would be getting say uh, two components.
Yes, 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 you are right. So are both the components light?
No, no, no. One is heavy and only one is light.
Correct, correct, correct. So one of this component is so many vertices. So this is definitely heavy. The other component is only two vertices. So root, the bag corresponding to the root is not a balanced separator. So then the algorithm proceeds. Then, okay, so one more thing. So look at the left subtree of the root. It has A, D, and S. So look at the left subtree and take the union of all the bags. So on the left subtree, the union of all the bags contains A, D, and S. So that is basically corresponding to A and this light component. Whereas this other subtree, the right subtree rooted at A, this is the union of the bags here is nothing but all the vertices on the other component. So that means this heavier component, because the heavier component is causing the problem, so we have to check if we can move to the heavier component and delete some bag from the heavier component. So therefore from root we traverse to the next child in the heavier side. So the root has two child, we will traverse to that child which is on the heavier side. So therefore next we try to delete the bag T2, that means the vertices A, B and C, and again we ask that whether we have found a balanced separator, so whether ABC is in fact a balanced separator or not. So if we delete ABC, do we, what are the components we get and whether all the components are light?
Yes. So if we remove ABC, then still we would be having one heavy component having GX3, Y, ZYH, having six elements. So probably while after removal of the bag, we should focus on the heavier component and whether the size of the heavier component is less than or equals to n by 2 or not, and other
Yes, yes,
components automatically will fall in the place.
that is
So
correct.
yeah, so if we remove ABC from here, then yes, I mean the largest component is having 6 elements here.
So the largest component is this. They have how many? One, two, three, four, five, six, 7 elements are there. Of course, seven is not allowed. At most, we can allow n by 2 by n by 2 floor, which is in our case 13 by 2 floor, which is 6. But here we can see there are 7 vertices in the heaviest component. So again, then we realize that okay, now from here, which direction shall we go? Shall we go in this direction or in this direction?
So we should move to the BQG part. BQG.
Yes, yes, yes. Because this subtree corresponds to this component. If you look at this subtree, you will see that the union of the bags is corresponding to this heaviest component. So now we ask that if we delete this T5 and if we delete these vertices in this bag, B, Q, and G, do we end up with all light components? So B, Q, and G are to be deleted. So let me clean up things. So we are deleting these three. Now, how many components we have and whether all the components are light, that means having less than equal to 6 vertices.
Yes, so this time we would be having components, and wherein the size of every component would be less than n by 2. Would be at the most 6. But I was thinking that I mean in this entire process, why don't we take the degrees of the vertices within the bag into consideration somehow? Like say if I include G as I mean as a part of the S, then definitely this is going to create I mean this is going to impact
Hmm.
more, right, in this process. But definitely BQG will create the components and the size of every component would be less than 6.
Yes, yes. So you are suggesting that instead of doing this algorithm, can we do something greedily? So can we scan the set of vertices and then identify the largest degree vertex and then try to delete it, or rather maybe try to find a separator that includes the vertex with the largest degree? So that could be a possible heuristic, but I do not know whether it is true that the largest degree vertex is always part of the balanced separator or not.
Yes, because this degree is such a heuristic and which fails many a time because I mean whatever I'm suggesting is based on the limited insight which I can think of. And quite
Hmm.
possible that in a very complicated graph, I mean graph possible wherein despite having the largest degree, a vertex may not become the part of a capital S.
Correct, 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 correct.
Yeah.
So, but maybe there is some way to ensure that it can be exploited. I do not know, but this is the tree decomposition based approach to finding the balanced separator. This is fail safe, and it has been proved in the video that a separator of size k plus 1 can be found. So, I mean,
And
at this,
yeah,
yeah, yeah, go ahead.
yes, so yeah, I found this algorithm. I mean, this way of getting the components pretty useful, and probably in this way we can find, I mean, the strongly connected components, and if the complexity of this algorithm is better, then getting the components. I mean, this is more or less like getting the strongly connected components only. and wherein the complexity was, I don't exactly, Husarazu was the name of the algorithm to get the strongly connected components. And I don't remember its complexity, but there we used to apply the DFS twice.
Correct,
So
correct, correct.
yes, so but then this seems to be a slightly better way of getting the components. Yes.
So are you talking about directed graphs?
Oh, so this is only for the undirected graphs, or will this work for the directed graph as well? This
No,
mechanism.
this is for undirected graph. Uh, so the tree decomposition is also for the undirected graph.
Okay, okay, okay. Yeah.
But you are right. So this is in a way finding components. So, but the primary thing is the motivation behind finding a balanced separator is that once you find the balanced separator, then once the graph is divided into two parts of roughly light, I mean, when the parts into which you divide the graph are roughly small, then you can sort of do some iterative algorithm. In some cases, you can do some recursion on the small parts. And if the balance separator is small in size, I mean, the smaller the better. Smaller separators are better, sort of. They disconnect the graph into small pieces, and then you have to do, while merging the solutions of individual pieces, you have to only worry about the vertices in the separator. So when the balance separator is small, then better algorithms can be designed. For example, local search algorithms use the concept of balanced separators, and there are many papers, many problems that use local search to find what is called polynomial time approximation schemes. So where a small balanced separator in the graph always helps. So in fact,
Yes.
yeah, go ahead.
So do we have some analysis of the complexity of constructing such a decomposition tree?
Oh, this how to find 3D composition. Okay,
Yes.
so I think this is something we discussed two lectures ago, but that was for either nice 3D composition or this other one. Uh,
So I was thinking that if the complexity of getting the tree decomposition is good, is polynomial, so then indirectly we found the most influential nodes in this network. So like say B, Q, and G here are the most
hmm.
influential nodes, and whose removal, I mean, will leave the entire thing balanced, and yeah, that thing. So that's good because probably if we think of the information diffusion in this network, the way information is being spread,
Mhm.
then probably these are the point, these are the hubs, I mean, which actually matters. And if we remove them, these are the, I mean, the prominent nodes in the network in one way.
Yes, yes, they ensure that connectivity is maintained.
Yes, yes, yes.
So it may not be the case that there always exists a balanced separator in a graph. I mean, there always exists. I mean, it may not be possible to find a small balanced separator in all graphs. So we know that for planar graphs, it is always possible to find uh, small balanced separators. So it is a very celebrated result. So if there is a graph G with which is planar, a planar graph G with n nodes, then there exists an order root n sized separator, balanced separator. So that can be exploited in many algorithms. Have been exploited already. So this is called this is the name. This is the planar separator theorem, but this is due to Tarjan LT. L is for what? LT79. Just a second. So this is due to Tarjan and another person. Uh, Lipton. So there's a paper. It's a celebrated paper. It is called a separator theorem for planar graphs. So this paper is by Lipton and Tarjan from the 1979, and it appeared in the Siam Journal of Applied Math. So this is a very highly cited paper. There they propose that there is a sublinear sized balanced separator for planar graphs, and that led to many algorithms in many setups. And that showing the existence of a planar graph immediately means that some algorithm will be feasible that will give some good approximations and other things. But it is not possible to find sublinear sized balanced separators in many graphs, non-planar graphs. There are some classes of graphs for which finding a sublinear sized balanced separator is possible. And there, in such cases, if you can sort of formulate your problem or express your problem in terms of a graph where such a property holds true, then the algorithm becomes immediate.
Yes.
Okay. And you are asking that what is the time complexity for finding such a 3D composition?
Yes, in case if it is polynomial.
I'll check. So the time complexity is generally order n to the tree width. So
And the tree bits would be a constant thing, or
no, it may not be constant. There could be large tree widths also. So we have seen some in the book in the videos we had seen some class of graphs for which uh, the tree width was large. Let me check if I can get something quickly. So tree width need not be constant. So for example, if there is a grid graph, so let me draw this. So a grid graph is like this. 1, 2, 3, 4, 5. So I'm drawing a 5 by 5 grid. So you can understand that if you want to, so this is not looking like a tree at all. This is a grid graph. So it is known that the tree width of a k cross k, tree width of a k cross k grid uh, is exactly k. Okay, so for k greater than or equal to 2,
Hmm.
so there is dependence. So number of vertices in the grid graph is k squared. So you can expect a tree width of root. So if the number of vertices is n in the grid, then the tree width is root n.
Yes.
So it is not independent of n. So there's some more nice things about connecting tree with grids. So there's something called this is a well-known thing. It's called excluded grid theorem, grid minor theorem also. Some people call it excluded grid minor theorem also. It says that if the tree width of G of a graph G is at least k times, oh sorry, not k times, k to the 4k square k plus 2, then G has, it is the other direction, then G has a k cross k grid minor. Okay. So that means, in other words, if there is a large grid minor, then it is witness and the tree width is also large.
Yes. So I forgot the purpose of using the tree decompositions. I remember the different tree decompositions we studied, but
So in this
so
case, so in this case, you can expect that in so if tree width, so this is a running time, which is fixed parameter tractable in the parameter tree width. That means if tree width of a graph is constant, then this entire part is a constant. Then this is a polynomial expression. So if you know that there is some graph for which tree width is constant, then in polynomial time, in fact, in this case, linear time, you can find a tree decomposition like this. Then if you can find a tree decomposition like this already, then with this simple algorithm, you can find a balanced separator also. So that is the use of doing this tree decomposition.
yes, yes, yes.
Okay, I think, yeah, let's move to the next question. So this is end of it. Yeah, so yeah, huh. I will let you read the question. This is about uh, finding, certain things have to be told. Okay, so g of x means, so in a graph g, x is a subset of v, and g of x is the induced, is a subgraph induced by x. Okay. So what is the meaning of that? So if I say that, okay, this is the set of vertices in x, then I take all the edges whose endpoints are lying in x. So if there is an edge like this, I must take it. But if there is an edge whose one endpoint is in x, other endpoint is not in x, then we don't take it. This I don't take. So the black vertices are assumed to be in X. The remaining ones are not in X. Okay. So now the question is, when is the subgraph induced by X connected? So there are certain options, and okay, so INC, okay, INC means incidence. INC E comma U means this is equivalent to saying that U is an endpoint, or I would rather write it as E is incident on U. I'll write like that. So edge E is incident on vertex U. That is to say, U is one of the endpoints of E.
Yes. So the first one says that yeah, actually these predicates are a bit difficult to read, but
Okay, so let me explain the predicates. Yeah, so I'll write down what is. So let's look at the first. Of course, you can see that the first option is the correct answer. The other options will also be taken care of. Just give me a moment. So I'm looking at the first option, and I'm looking at the left hand side. So this is, let us say, statement P, and this is, let us say, statement Q. So P implies Q. That is, so let us write in English what does P mean. So it says that for every subset Y of vertices, so I'll write it down, for every subset Y of vertices, so what happens? X, so X is given to you. X is the set of vertices on which you are inducing the subgraph. So X contains both a vertex from Y and a vertex from outside Y. Okay. So X contains a vertex from Y and a vertex from Y complement outside of Y. That is the first thing. So X is given to you. So what does this right hand side statement mean? We'll make some space. Okay, so there are three existential signs. There exists, there exists, there exists. So there exists an edge E whose endpoints U and V both belong to X. Okay, so U belongs to X, V also belongs to X. That is the three existential things are saying. So I'll write it down. So there exists an edge E whose both endpoints U and V are in X. So there is an edge uh, basically completely within X, but one of the vertices u is in y and the other vertex is outside of y. Okay. So because of this, but u is in y and v is outside y. So I'll say in y complement. Okay. So do you understand the English translation of the two statements P and Q?
Yes, translation is clear. Individually, the translation is clear.
All right.
Uh, but why this P is implying Q is not making sense.
Okay. So the question is, if you have a graph and additionally you are given a subset X of vertices, when will you know for sure that the subgraph induced by X is connected? So they are saying that, okay, G of X, that is the subgraph induced by X, is going to be connected if and only if P implies Q. So now let us read these two things as P implies Q. So what does P implies Q mean? It means that for every subset of vertices Y, if X contains both a vertex from Y and a vertex from outside Y, then there exists an edge which is completely in X, but one of its endpoints is in Y, the other one is outside Y. So they're saying that, okay, if Gx is connected, then definitely P will imply Q. Now, it is such a long statement, that is why I have taken an example. So consider this example. So this is my graph G, and suppose this is given to you X. Okay. So what is uh, 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 the subgraph induced by X?
Yes, so subgraph induced by X is, I mean, all the edges which are there within these four vertices will uh,
Yes.
will be considered.
So there are only two edges. So G of X is this two edges only. All right.
Yes, yes,
So 1, 4 and 6, 8. That's all. So now you can see that from this figure, Gx, the subgraph induced by X is not connected. So this is separate from this. There is no connection between 6 and 4. Okay. Uh, right. So now try to read this statement. So its statement says that for every y of vertices, X contains a vertex from Y and a vertex from Y complement. So let us try to find a Y such that X contains a vertex from Y and a vertex from Y complement also. Let us say, so let us say if I consider these four vertices to be Y. So let us say this is my Y, then P is true, that this vertex is in Y. So there is a vertex, these two vertices are in Y, but there are other vertices which are outside of Y in X. So this is a valid description of Y as per statement P.
yes, yes.
Okay. Okay. So now consider this is my Y. Now consider the statement Q. So there exists an edge E whose both endpoints U and V are in X. Okay. So this is that edge. There is but one of the so now let me write and draw it permanently. So this is my Y. So now they are saying that, okay, you should be able to find an edge in the graph whose both endpoints are in X. So that means you should be able to find an edge which is in the induced subgraph such that one of the endpoints is in Y, the other endpoint is not in Y. But in this case, we see that, okay, both the edges are I. So this edge which is part of the induced subgraph, is completely within Y, whereas this edge, which is part of the induced subgraph, is completely outside Y. So I cannot find an edge which is sort of going across from Y to outside Y. So this is,
Yes.
yeah. So no matter what you do, you cannot find a Y such that this statement Q can be made true. So this is saying that, okay, the subgraph induced by X is not connected. Okay. So P is not implying Q. Okay. So now you extend X. Now you include one more vertex in X. So I'm including 5 as well. So once I included 5, then what is the induced subgraph GX? Some more edges will be added.
Yes, yes. So then 4, 5, 8 will also get included. 5, 6 will also get included.
That is
Uh,
true.
yes, these two only.
So now GX becomes a connected subgraph. Now again we'll verify whether statement P implies statement Q. Okay. So what is statement P? Statement P says that for every subset Y such that uh, X, so for every subset Y of vertices, X contains a vertex from Y and a vertex from Y complement. Yeah. Uh, so these are my vertices within the X. So I'm taking this to be Y. So in this Y, there are vertices which are in X. Also, there are vertices. No, no, so I have to see X. So in X, some vertices are in Y. So these two vertices are in Y, and some vertices are outside Y. So this is a valid X. So I'm considering only those Ys for which this is true, that some of the X vertices are outside Y and some of the X vertices are inside Y. So this is a valid Y. So now this is the Y, then Q must be true. Now consider the statement Q. So you should be able to find an edge which is going across. You should be able to find an edge in the induced subgraph Gx, which is going across from Y to outside Y. Do you see any such edge?
4, 5.
Yes, yes. So that means P is implying Q. Okay, so you can realize that from this example, you can appreciate that P implies Q will only be true when G of X, that is the subgraph induced by X, is a connected graph.
Yes. Yes.
And I'll tell you, if you don't do any such thing, the other three options can be ruled out just by looking at them because they do not make any sense at all. So let us look at the other three. So first of all, let's look at the second option. So, so we want to find that which of these statements are equivalent to Gx being connected. So now you are going to say that G of X is connected if and only if, let us say, this statement is true. So now look at the left hand side. In the left hand side, there is no mention of X at all. It is saying that for all vertices in the graph, there exists a vertex in the graph such that there is an edge UV. So it is basically saying, so this part is basically saying that every vertex has degree at least 1. There is no isolated vertex. That's what it is saying. Okay, so there is no mention of X at all. So if you are characterizing Gx, then how can you make a statement which is independent of X? So this cannot be true. This is ruled out.
Yes.
Similarly, this is also saying the same thing, that for every vertex u in the graph, there is a vertex to which it is adjacent. Oh, no, no. For all, so for all vertices, oh, this is a complete graph. This is saying that for every vertex, every other vertex is adjacent to it. Okay. and it is not also saying u is not equal to v, so it is also assuming that every vertex has a self loop, and it is connected to every other uh, vertex in the graph. So there's a complete graph where, so this statement is saying that there is a complete graph. Additionally, every vertex has a self loop. Again, you are characterizing x, but there is no mention of x whatsoever. Then how can this be true? So how can this be equivalent to this statement? So again, this is ruled out. Now this one is again, so yeah, so spend some time on this and try to see what is the anomaly in this uh, option.
So it says that for all the y's, which are the set of the subset of the vertices, there exists a u which is the element of x, and then there exists a v which is the element of x. I mean, if I pick two vertices from within the subset x and the adjacent of uv, so I pick, so then I found the adjacents, I mean adjacent vertices of the u and v. Uh, I mean, this ADJ of UV implies what? The
It means
adjacency.
that even we are connected by an edge.
Oh, I see. I see. So okay. So if we pick any edge within the set X, then this implies that there exists U in the Y and there exists V in the Y. Also, this is not necessary that whenever there is an edge in between the X, then there should always be an edge in I mean in the subset Y as well. There is no such compulsion.
Yes, 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 yes. Yeah, so this can also be ruled out. So for all subsets, they are saying that whenever there exists an edge u comma v which is in x, and this implies that there exists an u comma v which is in y. So I mean, you can take a y. Uh, uh, s- okay, so how to rule this out formally? Let's think about it slightly. Uh, so this portion is saying that in y there is an edge. Okay, in y there is at least one edge among the vertices of y. Oh, that itself is, so for example, you could take these three to be y. Okay, and if you take these three to be y, that is not preventing the left hand side to be incorrect. So the left hand side is just saying that there is uh, some edge in the graph induced by x. But this one is saying that no matter what y is, there is some edge within the vertices of y. That doesn't make sense, because you could have taken y in such a way that they are forming an independent set. If you is that clear?
Yes, yes, it makes sense.
All
Uh,
right.
I mean, in this question, can you show again that I mean, what y and x are? In the beginning of the question, the definitions of x and y were given. Oh, yes, x was the subset of the set of the vertices and gx is connected. Yes, I understood this.
Yeah, so X is just a subset that is inducing a subgraph, and they're using Y to sort of characterize the connectedness of GX. It's a nice characterization, I think, because I mean, if somebody tells you that I'm going to give you X, and without even drawing the subgraph, you know that it is connected or not. Uh, this is nice, that whenever for every Y we check. So for example, we took this Y and we checked whether it has some vertices from x, some vertices outside x, and whether there is a edge going across. And then we realize that okay, this would mean that x itself is connected. Okay, so at this point we can take a short break.
Oh, yes, yes, sure, sure.
Okay, so let us take a short break. We will finish quickly today. So you can take a look at the third question. So in fact, I will show you. So there are five questions only overall to discuss in week 7. So this is 624. And after the break, I think the next three questions are going to take at most half an hour. So I think we can start. What time shall we take a 10 minutes break now?
Sure, sure, sure.
Okay, okay. So let's,
6:35.
yes, 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 yes. So we'll start taking at 6:35. So by 7 o'clock or so, we should be finished.
Okay, sure, sure.
Can you hear me?
Yes, yes, I can.
Okay, so let's start again. So this is the question. I hope you had a chance to read the question. So what do you think?
Yes, so can you tell me the meaning of this inc e comma e? Does this mean that that the vertex u is incident on u, e is incident on u, or u is incident on e?
So it means that, for example, incidence u means there is a vertex u and there is an edge e which is incident on u.
The first one says that so and the meaning of adj u comma v is that there is connectivity in between u and v. There is an edge in between u and v. Is
Yes,
this
yes,
okay? So then the first option is that if there is an edge in between u and v, then u is not equals to v. Is okay, and there exists an edge e such that inc e comma u, and but then this second e could be different from the first one, so there is no guarantee that the same e
yes,
is incident on u as well as on v.
yes,
And yeah, and however, in the second option, there is a guarantee that the same edge E is incident on U as well as on V. So thereby implying that there is a connectivity in between U and V. And so regarding the third one says, I mean, also suffers from the same problem that the E could be different in both the uh,
mhm,
formulas. And last one is okay, but that it does not guarantee anything. Does not guarantee connectivity actually.
yes, yes. So you got it right. In fact, you have deciphered all the options. So, and you are right that in this option, because it says that u and v are different vertices, and there is exactly an edge. There exists an edge which connects u and v because of the incidences. So there is an incidence of e on u as well as the same is incident to v. Means that u and v are definitely adjacent. Whereas in the first option, one would be tempted to also consider the first option where it says that there is some edge which is incident to E and there is some edge which is incident to V. So it may possibly happen that there is an edge like this and there is an edge like this, but that doesn't guarantee a direct edge between U and V, which we want in edge UV. So therefore, this is the correct answer. So you are right. Fine. This is also not too difficult. So what is an independent set? An independent set is
So
a
in the,
set of vertices. Yeah, go ahead.
yeah, yeah, in which no vertex is connected to every other vertex in that subset. Yeah, in that set.
Yeah, an independent set is a set of vertices such that no two vertices have an edge between them. So now you can think about the correct option and why the others are incorrect.
Yes. So if X is an independent set, so then there exists U comma V. I mean elements of the set X, such that there is connectivity between U and V. So since X is an independent, so it cannot happen. And the
Yes.
second option is that X not. So clearly, if U and V are the elements of the set of the independent set, so there cannot be connectivity in between U and V. So the second option is correct, even it is, I mean, written below in the answer. And third one is that for all U's and the V's, there should be connectivity. It can never be true. However, regarding the fourth one, it says that for all U's and V's, which are the elements of X, for all the vertices, U and V here are the elements of the set of the subset of the vertices. So for all vertices, there does not exist connectivity in between U and V. This seems to be true. However, U there would be a possibility wherein U is connected to, I mean, I don't know, but in the case of uh, this thing, so yes, so the second option was that there exists U and V. So it shows that this is weak. So the last one seems to be fine. The second option only says that there exists only one pair of the
Yes,
vertices that we do not have connectivity. However, the last
correct.
one says that for all the pairs of the vertices, there should not be any connectivity. So yeah, this truly reflects, I mean, the meaning of X, the
Yes, yes.
independent.
So the second one is also tempting, but it is saying that one pair, there exists one pair of vertices such that they don't have an edge in between. So for example, if I identified these vertices in a graph, suppose this circle or ellipse that denotes the graph, and I identified some of the vertices, and let us say this is an independent set, then it should be the case that for every pair of vertices, there should not be an adjacency. Every pair, there should not be any edge. Whereas this is saying that there is one pair for which there is no edge, but other pairs, even if there are edge, they are allowing it. So that means independence is not guaranteed by this option. Whereas this is guaranteeing independence because for every pair of vertices in X, it does not allow an edge. No adjacency, not ADJ. This is not. Therefore,
Yeah.
this reflects that X is an independent set. Hence, you have correctly identified it. Okay. So this is the last question for today. Okay, so this is let you read it, but this is more like true and false kind of thing.
Yes, so which of the following statements are true? A graph G has tree width of less than or equals to 2 if and only if G is a subgraph of a series of the parallel graph. So I did not understand its meaning. And the
Yes.
second one is that for every k greater than or equals to 2, the tree width of k cross k grid is exactly k plus 1. So you, I mean, told this thing in the beginning of the session. So this seems
Yes.
to be true. And every planar graph with the tree width greater than 4k has this minor. So I do not understand this minor term here. And
Mhm.
in the last option, also the minor term is there. Yes.
Okay. So a series parallel graph. So in the first option, there is term called series parallel graph. So that I do not. I will show you an example. So you remember this connecting resistors in series and connecting resistors in parallel, that kind of thing in electrical. So if the vertices are sort of like this, so there is some parallel connections, but there is some series connection also. So we say that okay, so these things are sort of in series, but this piece and this piece are in parallel. So that kind of graph, although I do not know what is the formal definition, but in the video I saw this example. This is an example of series parallel graph, and it is a fact that the tree width of such a graph is at most 2. So therefore this is correct. And for a k cross k grid, so as I said, if there is a k cross k grid, k by k, then the tree width of such a k cross k grid is exactly k. Whereas it is saying that tree width is exactly k plus 1, that is incorrect. Now,
Yes,
every,
yes.
yeah, every planar graph with tree width greater than or equal to 4k has a k cross k grid minor. So remember that the grid graph is also a planar graph. It is possible to draw it on the plane without the edges intersecting each other, except at the endpoints. So let's talk about the minor thing first. So minor is, so I'll define this. So in graph theory, a minor of a graph G is another graph H that can be formed from G by a series of specific operations. So H will be called a minor of G if H can be obtained from G via a series of operations. So one is vertex deletion. So you delete some vertex. Of course, when you delete a vertex, you also have to delete the edges incident on the vertex. Edge deletion is simply deletion of an edge. Does not require deleting the vertices on which the edge is incident. The other thing is edge contraction. So edge contraction means you pick an edge E, suppose you pick an edge E and you contract it to one vertex. So you make it one vertex UV, and all the edges that were incident to U as well as V, you make them incident to UV. So this is the edge contraction operation. So with the help of these three operations, if you can get H from G, then you will say that H is a minor. All right. Is it fine? What is the definition of a minor?
Yes, can you repeat this thing? Actually, I could not. There
Okay.
was an issue in the connectivity, so I could not hear you properly.
So I'm describing this operation of edge contraction. So suppose you pick an edge E which is incident to two vertices U and V, then the edge contraction operation is removing the two edges U and V and replacing it with an super node, super vertex UV, and additionally all the edges that were incident to U and to V are now made incident to this new vertex UV. So if you do that
Yes.
operation, you will
Yes.
reduce the number of vertices by 1. You will also reduce the number of edges by 1.
Yes.
Okay, so now let's look at this option. So every planar graph with tree width greater than equal to 4k has a k cross k grid minor. So let me check if that is true. Yeah, so if this is a fact that every planar graph with tree width at least 4k has a k cross k grid minor. So this is a fact. I do not know how to prove it. It is also treated as a fact in the lecture. And the last option, if f is a minor of G, then the tree width of f is less than, this is believable. That the minor of G is sort of contracted form of G. It's less than
Yes.
G, then its tree width is also going to be less.
Yes.
So maybe there is a formal way to prove it, but I will accept it on the basis of intuition. So these three options A, B, A, C, and D are correct. Okay. So this is all that we have. So in this session, we have covered 5 assignment questions, or rather, I'll say all the 5. All 5 assignment questions of last year's us week, or is it week 7 assignment. So at this point, we can conclude. Or if you have anything to ask, I am free for discussing. If there is any doubt, you can ask me. Anything you want to make comment or anything, you can ask me. I'll be here another 5-10 minutes, or we
So
can conclude.
yeah, so
Yes,
what will be the topic of the next session in the week 8 or
yes, yes. Let me check. So this is, oh, so there is some DP as well as some integer linear programming based algorithms.
oh, this topic seems to be pretty interesting. Yeah, yeah.
Yes, yes,
Yes. Please share these notes also in the Google Drive. The way you
yes, yes,
you
yes. I'll do it right away.
yeah. Thank you so very much. Thank you,
All right,
Siddharth.
thank you. Thank you. Okay, take care.
Yeah. Bye bye.
Bye. So rest of you, if you have any questions, you can ask me.